Hello and welcome to notes for section 6.1a. Today this is where we talk about monomials and polynomials and the difference between those two. First we'll start with a monomial. A monomial is a single term. That's why you see the mono or M-O-N-O. Generally when we talk about a monomial, we're talking about a single term that actually contains both a variable and sometimes a coefficient. It doesn't have to have a coefficient, but a lot of the times it will. It's definitely going to contain a variable though. So for example, a constant is not a monomial because it's just one number by itself. A monomial contains a variable, which means that we've got multiplication happening generally of a variable. A polynomial is very similar to a monomial. It's just that a polynomial is like a collection of monomials being added or subtracted. So if you have a bunch of different terms that are being added in a row to create an expression, that's going to be a polynomial generally. And so we kind of think about how monomials come together to create polynomials through the operations of addition or subtraction. You've heard us talk about standard form before, but today specifically when we think about standard form, it means that we are writing a polynomial's degree from highest to lowest. And you might be thinking, well, what does that mean? It's just another fancy word for when we have an exponent. So you can think about degree and exponent as being exactly the same thing because essentially they are. Every expression that we have from here on out, we'll be able to refer to it by the number of terms that are in the expression and also the degree of the expression. So for example, if you have x to the 0 power, that's just going to be 1. That's a constant. It means that you're not actually dealing with a variable, and so it's not really a monomial. That would be like the number 12. When we have x to the first power, and that's when you have one value of x by itself. It's not being multiplied by itself or anything, and that's going to be a linear function. We've traditionally seen those with y equals mx plus b. If it's x to the second power, it's called a quadratic function, and this is actually what we're going to spend all of Unit 7 doing, is working with quadratic functions, but that's when your exponent is 2. From here, we just kind of start to think about what the exponent would do as it changes. So x to the third power would be cubic because when we multiply a value by itself 3 times, it's cubed. To the fourth power, x to the fourth power would be quartic. So quadratic, you might think, sounds like quartic, but the fourth power is quartic. For the fifth, I want you to think of like a quintet. X to the fifth power is the quintic degree or the quintic power for a polynomial. If it's a number larger than that, you're usually just going to use the letter n and call it an nth polynomial or a polynomial of nth degree. So like 10th degree polynomial, or this is a polynomial of the 10th degree. That's just specifically talking about what the largest exponent is. So when we talk about degree, that's exponent. The number of terms is going to be how many actual terms are in the expression. So if it's just a variable by itself, just one thing all alone, this is an example of a monomial, but there will be a variable. This is different than a constant. If there are 2 terms, so like you have x plus 3 or 2x plus 9x or something like that, that's a binomial because there are 2 terms that make the expression. If mono is 1 and bi is 2, then it would make sense that if there are 3 terms, that it is a trinomial. In all of these, the only thing that's changing is the prefix in front of the nomial suffix. If there are more than 3, we don't have a specific term. We're just going to call it a polynomial. It doesn't mean, it's not like, okay, there are 4 terms, so we call it a quadrinomial. That doesn't happen. If there are more than 3, you're just going to call it a polynomial. And generally when we write a polynomial in standard form, it's always going to go in order by degree, highest to lowest. So that's why the examples, that's why I wrote them in the order that I did. Let's classify. So example 1 has you finding the degree of each monomial, and we know that degree means the highest exponent. I didn't mean to highlight that. That's okay. The highest exponent in number 1 is 2 because 2 is a coefficient and doesn't really have an exponent. It has a 1, and then y has an exponent of 1. When the degree of a term of the monomials here is 2, it's a quadratic degree. So that's second degree quadratic. Number 2 is an example of a constant. So when I'm looking at this, I'm noticing that there isn't an x value, which means that it would be x to the 0. And when that happens, it's a constant because I don't have any variable. This is not the same as a monomial, although technically you could call it a monomial if you wanted to. Look at question number 3. I have 4 different variables, each with 1 as their degree. It doesn't matter that the letters are different. This is still a linear function because, or a linear polynomial, I guess, or a linear monomial. Whew, a lot of words there. Still linear because the leading degree is still 1, even though they're different letters and variables added together. All right, number 4. 4 says 4b to the third c. That the only exponent you have is 3, and that leads to a cubic function. All right, let's look at example 2. We've got 5 through 10 here. It's asking you to classify the polynomial by degree and number of terms. So look at number 5. The degree is 2. It's the highest exponent. And so that means that it's a quadratic polynomial. I haven't figured out how many terms there are yet, so I'm going to write quadratic first. Now we have to count 1, 2, 3 terms. When there are 3 terms, I use the prefix tri for trinomial. I don't really have room for that, so I'm just going to abbreviate it. Number 6. K squared plus 64 minus k plus 7k to the third power. Even though it's the very last term, the degree is still a 3. It doesn't matter what order they're in. They're just not in standard form. And then there are 4 terms. So when there are more than 3 terms, we just call it a polynomial. Cubic because the leading degree is 3. And then polynomial because there are more than 3 terms. Number 7. On number 7, we have 4x squared and then a positive 3x. So our leading coefficient, or not coefficient, excuse me, our degree is going to be 2, which makes it a quadratic polynomial. And I don't know how many terms yet, I haven't counted. 1 and then 2. So 2 terms means binomial because I only have 2 terms instead of 3, and then there's still more than 1. Number 8. On number 8, we have 24 minus n to the third power plus n. So this time the n to the third power is our degree, which makes this a cubic polynomial or cubic expression. And then there are 3 terms. So instead of calling it a polynomial, I'm going to say it's a trinomial because that's how many terms there are. Number 9. On number 9, we got a lot going on, but you'll notice that the highest degree that you have is a 3, whether it's an a to the third or a b to the third. It doesn't matter what the variable is that has the highest degree. It just matters that you know when it's a 3, it's cubic. And this time there are 4 terms, so instead of calling it a trinomial, it's a polynomial because that's the word we use for more than 3. A lot of terms there. And then look at number 10. So number 10, there's definitely a variable, and even though you can't see the exponent, it has a 1. And when the exponent is 1, and that's the degree that you're dealing with, it's talking about a linear function. So imagine graphing like y equals negative 2x. And then this is a single term. There's only 1 term, no addition or subtraction. So linear, monomial. And there's the first page. Let's do some work on the second page. Here we're combining like terms. We're going to do this 2 ways. The first way is horizontally and the second way is vertically. You get to decide which method you prefer. The first thing that I want to do when I'm combining like terms is identify what the like terms actually are, and then I want to write them together. So the expression starts out with a 4x to the third, and I notice that there's another x to the third power. You can't see the 1, but I'm going to write the 1 in front of it just as a placeholder. Next, I'm going to go back to my first expression, and I see an x to the second power. That's the next highest exponent, so I'm going to go ahead and I'm going to write that down. I also noticed that the second expression has a negative 3x squared, so those will both be like terms. When it comes to finishing this off, though, I have a positive 7x in the second expression, but the first expression has a negative 5. Those are not like terms, so I need to make sure that those are in different colors. And I color-coded so that I can just add the coefficients here. 4 and 1 make 5, and then I just copy on the x to the third. 1 minus 3 is negative 2, and I copy down the x to the second power. And then 7x and negative 5 are not like terms. So I can't actually combine anything there, and that's my final answer, is 5x to the third minus 2x squared plus 7x minus 5. This is the traditional way we combine like terms, but if you want to use the vertical format, you'd more like to line them up vertically, like a more traditional addition problem, that's definitely a different way to solve it. So the way that you would do this is you would say, well, the first expression was 4x cubed plus x squared minus 5. And what we add is going to go directly below vertically and make sure that your like terms line up. So I put the x cubed underneath the other x cubed. I'm going to put the x squared underneath the other x squared. And then I want you to notice that the negative 5 and the 7x are not like terms. So what I'm going to do is be really, really careful here and make sure that I'm paying attention to the fact that I don't have a constant, but I do have a variable. So just to keep everything in order and like terms together, I went ahead and I put a 0 as a placeholder. When I add straight down, 4x to the third plus 1x to the third is 5x to the third. So I'm combining the like terms straight down instead of straight across. Next, I have the x squareds. It's 1x squared minus 3x squared, and 1 minus 3 gives me negative 2. So once again, I end up with a negative 2x squared. So far, this process is giving me the exact same answer as the process above. And it doesn't really matter how you do this, all we're doing is combining like terms. It gets a little bit tricky when you don't have like terms, so I had to put the 0 in as the placeholder. You didn't have to do it this way, but I didn't want to get myself confused. So I put a 0 in there to remind me that negative 5 plus 0 is just negative 5, and that negative 5 and 7x are not like terms. I could have written another 0 after the 5 in the first row, but I didn't really feel the need to. You get to decide which method you like. You can do either one for addition, pretty straightforward. When we subtract expressions, though, we have to make sure that we're paying attention to what's positive and what's negative. So I'm going to copy down this first expression, which isn't anything different, it's just original. But what's happening here is that subtracting this entire set of parentheses is actually the same as distributing a negative 1 to the whole second expression. So what I did is I replaced the negative 1, I made it addition, and then I wrote that what we're really doing is distributing that negative 1. Because what's going to happen now is all of these terms in the second expression are going to go ahead and change value. So copy down 4z squared and negative 3. Now I have to distribute. Negative 1 and negative 2z squared make positive 2z squared. Next, negative 1 and positive 5z make negative 5z. And then the last term is negative 1 and negative 1, and together those make positive 1. I've done the distribution, awesome. I'm ready to identify the like terms and then actually combine those like terms. So I have to figure out where my like terms are. I start out by looking for exponents that are the same. I have a 4z cubed, or squared, sorry, and a 2z squared. Since those both have the exact same variable and exponent, I can add the coefficients and get 6z squared. Next, I have a negative 5z, but it's actually the only term I have that has a single variable with no visible exponent. So I'm just going to copy that one down. I do have two constants that can be combined. There's a negative 3 and a positive 1. Negative 3 plus 1 is negative 2. So to finish off my expression, I'll copy down the negative 2. And those are all of the like terms, and I can't combine this any further, so this is my final answer. If you like the vertical method, I'm still going to remind you that you need to make sure all of your like terms are actually in order. So 4z squared minus 3 is missing that placeholder, or not placeholder, a term that would be in like the z component. We don't have a z for that first term, so when I write down the second expression, I want to make sure that all of the terms that are alike are next to each other. So instead of writing this in the traditional order, I'm actually going to change it so that the negative 1 that's now positive because I distributed, I'm going to go ahead and change that so that all of my like terms are right by each other. I did also go ahead and distribute, so everything that was negative is now positive and everything that was positive is now negative. And it's time to just add straight down. So the z squareds get added, and I have 6 of them. Then my constants, -3 and +1, those end up giving me -2. And then the -5z doesn't have any like terms. So you can see that even though the order might end up looking a little bit different, you do end up having the exact same answer for both of these, regardless of which method you choose. And that's why you just get to kind of decide, do I like this? Do I like this? It's up to you. All right, let's do some practice here. Combining like terms. First, look for all of the exponents and variables that are the same, and then we're going to combine them. So I have x squared and a +3x squared, and I want to color code these, so I'm going to use the same colors and with the highlighters. Both of these are positive, so I don't have to worry about any negative numbers yet, but as I go along trying to combine, I do see two negative numbers here. So this is a -4x and a -3x. Those are my next set of like terms because they both have a variable and the exponent is just 1, invisible really, you can't really see it. And then last is my constants. I have a +3 and a -5. So I need to make sure that I'm always writing down exactly whatever the value is. You're not changing anything. I haven't even done any math right now. I'm just rewriting in a different order. This is when I start to calculate though, because if they have the same variable and exponent, I can combine them. So 1 + 3 is 4, which means I have 4x squared. -4 minus 3 is -7, which means I have -7x. And then 3 minus 5 is -2. I don't have any other like terms, so that's my final answer. If you want to circle it, you're more than welcome to. I didn't this time though. Okay, what about number 12? On number 12, I'm going to start out by copying the first expression because there's not anything weird happening to that. What's weird is what happens in just a second. So the negative that's in front of that set of parentheses is actually meaning that the whole parentheses is being multiplied by -1. So -1 times 3r squared is -3r squared. -1 times 5r is -5r. And -1 times -1 is +1. So I have officially distributed that negative all the way through, and I am good to go. All right, next, I need to combine some like terms. So I've got 8r squared and -3r squared, and those are my two like terms for the r squared. The next thing that I'm looking at is I have a -12r and a -5r. Those both have a variable r, and neither one has an exponent, so I can combine those like terms. And then last but not least, I have to look at my constants here. Oh, that was not the right color. Let's see if I can fix that. There we go. When I add the constants, I have 4 and 1 being added together. Those are both positive, so I'm just going to do +4 and then +1. At this point, all I've done is written all of your like terms together, so I'm finally ready to combine. 8r squared minus 3r squared is 5r squared. -12r minus 5r is -17r. And 4 + 1 is 5. There are no more like terms here, so you can't combine anything, and that's your final answer. The other two problems, 13 and 14, the answer key is on Canvas.